Welcome to the Deep Sleep Discoveries channel. Tonight, we journey together toward our closest star, that blazing sphere of light that has warmed Earth for billions of years. As you settle into comfort, let these facts about the Sun wash over you like gentle waves, each one a small wonder to contemplate as you drift toward peaceful rest, connected to the cosmic dance that unfolds above us every single day. Before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, please consider liking and subscribing to the channel. It helps others find their way here too. The Sun is classified as a yellow dwarf star, and while modest compared to stellar giants, it actually ranks in the top 10% of stars by mass in our galaxy, where smaller red dwarfs far outnumber stars like ours. This means our Sun, though we call it ordinary, is actually more massive and luminous than the vast majority of stars scattered throughout the Milky Way. In a galaxy populated mostly by dim, cool red dwarfs that burn their fuel slowly over trillions of years, our Sun shines as a beacon of medium warmth and brightness, neither the smallest ember nor the most furious inferno, but a steady, reliable presence in the cosmic landscape. The Sun contains 99.86% of all the mass in our entire solar system, a staggering concentration of matter that speaks to its gravitational dominance over everything that orbits it. All the planets combined, from tiny Mercury to giant Jupiter, along with every asteroid, comet, moon and speck of dust drifting through space, account for less than a fraction of a percent of the total mass. This immense gravitational pull holds our solar system together, keeping Earth in its life-sustaining orbit and Jupiter in its distant path, maintaining the delicate cosmic choreography that has persisted for billions of years, all centered on this single blazing star. The Sun is approximately 4.6 billion years old, middle-aged in stellar terms, having already lived through roughly half of its expected lifespan as a main sequence star. It formed from a vast, rotating cloud of gas and dust, and since that ancient beginning it has burned steadily, providing light and warmth to our corner of the galaxy. In human terms, if the Sun's total life were compressed into a single day, we would currently be somewhere around noon, with the morning's youth behind us and the afternoon's maturity stretching ahead, a reassuring thought that our star will continue to shine reliably for billions of years to come. It formed from a collapsing cloud of gas and dust called a solar nebula, a vast, slowly rotating mass that began to compress under its own gravity about 4.6 billion years ago. As this nebula collapsed, it spun faster, flattening into a disk with a dense center that would become our Sun, while the remaining material in the disk eventually coalesced into planets, moons, and asteroids. The process was gradual, taking perhaps a few 100,000 years for the core to heat sufficiently to ignite nuclear fusion, transforming a dark, cold protostar into the brilliant, life-giving sphere we see today, a transformation that marked the true birth of our solar system. The Sun is roughly 109 times wider than Earth in diameter, a scale that challenges our everyday understanding of size and distance. If you could line up Earths side by side across the Sun's face, you would need 109 of them to span from one edge to the other, each of our entire world reduced to a small segment in that vast expanse. This measurement speaks to the enormous physical presence of our star, a sphere so large that it dominates the sky of every planet in our solar system, its light reaching across millions and billions of miles, warming worlds and illuminating the darkness of space with its steady, ancient glow. About 1.3 million Earths could fit inside the Sun's volume, a number that transforms our understanding of scale from the abstract to the nearly incomprehensible. Imagine our entire planet, with all its oceans, mountains, forests, and cities, as just one small marble among more than 1 million identical marbles packed inside that glowing sphere. The Sun's volume is so vast that it could contain our world over and over again, millions of times, and still have room to spare. This immense interior space is filled with roiling plasma, heated to extraordinary temperatures, a furnace of fusion that has burned without pause for billions of years. The Sun's diameter measures approximately 864,000 miles across, a distance so great that traveling it at highway speeds would take years of continuous driving. To put this in perspective, you could fit nearly 10 Jupiters side by side across the Sun's width, or more than 100 Earths in a straight line from edge to edge. This measurement represents not just physical size but the fundamental scale of stellar objects, reminders that stars are not merely bright points of light but enormous spheres of incandescent gas, each one a world unto itself, blazing in the darkness, holding court over any planets fortunate enough to orbit within their gravitational embrace. Its mass is about 333,000 times that of Earth, an extraordinary concentration of matter that creates the powerful gravitational field holding our entire solar system together. This mass consists almost entirely of hydrogen and helium, the lightest elements, yet compressed so densely in the core that nuclear fusion becomes possible, converting mass directly into energy according to Einstein's famous equation. Every second, the Sun converts millions of tons of its own mass into pure energy, light, and heat that radiate outward. Yet even with this constant loss, the Sun's mass remains so vast that it will continue burning for billions of years without noticeable depletion. The Sun accounts for 99.86% of the solar system's total mass, leaving all the planets, moons, asteroids, comets, and dust to share the remaining tiny fraction. This dominance means that when we think of our solar system, we are essentially thinking of the Sun itself, with everything else as mere accessories orbiting in its gravitational field. Jupiter, the largest planet, contains most of the remaining mass, yet even mighty Jupiter is dwarfed by the Sun's enormous presence. This lopsided distribution of mass shapes everything about our cosmic neighborhood, from the paths planets follow to the very stability of the system over billions of years. Light from the Sun takes an average of 8 minutes and 20 seconds to reach Earth, though this varies from about 8 minutes and 10 seconds at our closest approach to 8 minutes and 27 seconds at our most distant point in Earth's elliptical orbit. This means that when you look at the Sun, you are seeing it not as it is right now, but as it was slightly more than 8 minutes ago, a small glimpse into the recent past. The light that warms your face on a sunny afternoon began its journey at the Sun's surface over 8 minutes earlier, traveling across 93 million miles of empty space at 186,000 miles per second, arriving at last to illuminate our world. The Sun is made of approximately 73% hydrogen by mass, the lightest and most abundant element in the universe, the fundamental fuel that powers every star's nuclear furnace. This hydrogen exists as plasma, a state of matter so hot that electrons are stripped from their atoms, creating a sea of charged particles that flow and churn throughout the Sun's interior. Each hydrogen nucleus is simply a single proton, and in the Sun's core, these protons collide with such force that they overcome their natural electrical repulsion and fuse together, creating helium and releasing tremendous amounts of energy in the process, energy that eventually reaches us as sunlight and warmth. Helium makes up about 25% of the Sun's mass, the second most abundant element, created continuously through the fusion of hydrogen in the star's blazing core. Helium gets its name from Helios, the Greek god of the Sun, because it was first discovered in the Sun's spectrum before being found on Earth, a fitting tribute to its stellar origins. As the Sun ages, the percentage of helium gradually increases while hydrogen decreases, slowly transforming the star's internal composition. This helium forged in the nuclear furnace at the Sun's heart will one day become the fuel for a new phase of fusion when the hydrogen runs low billions of years from now. The remaining 2% consists of heavier elements like oxygen, carbon, nitrogen, iron, and dozens of others, elements forged in earlier generations of stars that exploded as supernovae and scattered their enriched material into space. These elements, though present in small amounts, are crucial because they were the building blocks for planets, including Earth, and ultimately for life itself. Every atom of carbon in your body, every oxygen molecule you breathe, every iron atom in your blood was created either in the heart of an ancient star or in its explosive death throes, making us quite literally children of the stars, connected through chemistry to the cosmos. The Sun contains enough hydrogen to continue burning for another 5 billion years, a reassuring timeline that stretches almost incomprehensibly far into the future, well beyond the entire history of life on Earth. This remaining fuel supply exists primarily in the core, where temperatures and pressures are high enough for fusion to occur, converting hydrogen into helium at a rate of about 600 million tons every single second. Despite this enormous consumption, the Sun's vast reserves of hydrogen mean that it will continue shining steadily, barely changing in brightness or temperature, providing stable conditions for Earth and the other planets for billions of years to come, a cosmic gift of time. Every second, the Sun converts about 600 million tons of hydrogen into helium, a staggering rate of transformation that has continued without pause for 4.6 billion years and will continue for billions more. This conversion happens through a multi-step process called the proton-proton chain, where hydrogen nuclei slam together with such force that they fuse, releasing energy in the form of gamma-ray photons and creating helium as a byproduct. Despite converting 600 million tons every second, the Sun's total mass is so enormous that this loss is barely noticeable, representing only a tiny fraction of its total fuel supply, ensuring its steady burning for the vast stretches of time ahead. The Sun's core temperature reaches about 27 million degrees Fahrenheit, a heat so extreme that it exists nowhere naturally on Earth and challenges our ability to comprehend such intensity. At these temperatures, matter exists only as plasma, with atoms moving at tremendous speeds, colliding with such force that nuclear fusion becomes not just possible, but inevitable. This is where the Sun's energy originates, in this compressed, superheated center where the pressure equals 250 billion times Earth's atmospheric pressure at sea level, crushing hydrogen atoms together and releasing the light and warmth that sustains life on our planet, energy born in an inferno beyond imagination. The surface temperature is approximately 10,000 degrees Fahrenheit, dramatically cooler than the core, yet still hot enough to vaporize any known material instantly. This visible layer, called the photosphere, glows with the yellow-white light we associate with our Sun, and from this relatively thin shell, most of the Sun's visible light escapes into space. The temperature difference between the core and surface is vast, representing a gradual cooling as you move outward from the nuclear furnace at the center. Despite being called the surface, the photosphere is actually a layer of gas with no solid boundary, simply the level where the Sun becomes transparent enough for light to escape. The corona, the Sun's outer atmosphere, mysteriously reaches temperatures of several million degrees Fahrenheit, far hotter than the surface below it, a phenomenon that puzzled scientists for decades and remains an active area of research. This seems to violate our everyday understanding that things should get cooler as you move away from a heat source, yet the corona defies this expectation spectacularly. Scientists believe that magnetic field lines threading through the corona carry energy upward from below, heating this tenuous outer atmosphere through processes involving magnetic reconnection and waves of energy rippling through the plasma, creating this paradoxical temperature inversion that makes the Sun's crown hotter than its face. The temperature decreases from the core outward through the radiative and convective zones, dropping from 27 million degrees to about 10,000 degrees at the surface, then paradoxically increases again in the corona above. This temperature profile creates distinct layers within the Sun, each with its own characteristics and physical processes. The journey from core to surface represents a gradual cooling as energy slowly works its way outward, taking thousands of years to make the trip. Yet above the photosphere, something changes, and the temperature begins climbing again, reaching into the millions of degrees in the ghostly corona, a mystery that reminds us how much we still have to learn. The photosphere, the visible surface, maintains a relatively cool 10,000 degrees Fahrenheit, a temperature that defines the Sun's color and the wavelengths of light it emits most strongly. At this temperature, the Sun produces a continuous spectrum of light, with its peak output in the yellow-green portion of the visible spectrum, though it emits light at all wavelengths from radio waves to X-rays. This is the layer we see when we look at the Sun, though of course we should never look directly at it without proper protection. The photosphere is where light finally escapes after its long journey from the core, beginning its 8-minute voyage across space to Earth. The Sun produces energy through nuclear fusion in its core, a process fundamentally different from the chemical burning we experience on Earth. Nuclear fusion occurs when atomic nuclei combine to form heavier nuclei, releasing tremendous amounts of energy in the process according to Einstein's equation E equals mc squared, which tells us that a small amount of mass can be converted into an enormous amount of energy. In the Sun's core, hydrogen nuclei fuse to create helium, and the slight difference in mass between the hydrogen going in and the helium coming out is converted into pure energy. Energy that eventually reaches us as warmth and light, the power source for virtually all life on Earth. It generates about 386 billion megawatts of energy every second, a number so large that it loses meaning in human terms, representing more power than humanity could ever hope to use. This is the Sun's luminosity, the total amount of energy it radiates into space in all directions, with only a tiny fraction intercepted by Earth despite our planet's size. To put this in perspective, in a single second, the Sun produces more energy than human civilization has used in its entire history. This steady, reliable output has remained remarkably constant for billions of years, providing the stable energy source necessary for life to evolve and thrive on our planet. This energy output equals approximately 91 billion gigatons of TNT exploding every second, an almost incomprehensible release of power that continues without pause, day after day, year after year, for billions of years. A single gigaton of TNT is equivalent to 1 billion tons, and the Sun releases 91 billion of these every single second in the form of light, heat, and other electromagnetic radiation. Yet, despite this violent energy production, the Sun appears serene from Earth, a steady disk of light that rises and sets with comforting regularity. This paradox between the Sun's violent interior processes and its calm exterior appearance is one of the wonders of stellar physics. More energy from the Sun reaches Earth in 1 hour than humanity uses in an entire year, a humbling statistic that highlights both the Sun's power and our relatively modest energy needs by cosmic standards. The Earth intercepts only about 1/1000th of the Sun's total output, as most of the Sun's energy radiates away into space in all directions. Yet even this tiny fraction is more than enough to power our weather, our oceans, our plant life, and potentially all our technological needs if we could capture it efficiently. This is why solar energy holds such promise as a renewable resource, tapping into a power source that will outlast our civilization by billions of years. The Sun has been shining for 4.6 billion years and will continue for billions more, a timeline that encompasses the entire history of our solar system, from its formation to the present day, and stretches forward into an almost unimaginable future. During this time, the Sun has remained remarkably stable, varying in brightness by only about 1% over its lifetime, providing the constant conditions necessary for life to emerge and evolve on Earth. This stability is a testament to the self-regulating nature of stars, where increases in fusion rate lead to expansion and cooling, while decreases lead to contraction and heating, creating a natural balance that maintains steady energy output across billions of years. The core extends about 25% of the way to the Sun's surface, occupying roughly the innermost quarter of the Sun's radius, yet containing more than half of the Sun's total mass due to the extreme compression at the center. This is the only region where conditions are extreme enough for nuclear fusion to occur, where temperatures exceed 27 million degrees and pressures reach unimaginable levels. Outside this core, the Sun still glows with tremendous heat, but the fusion reactions that power everything happen only in this compressed central region. The core is where the Sun's story truly unfolds, where hydrogen becomes helium and mass becomes energy, the furnace that has burned for billions of years. Nuclear fusion occurs exclusively in this dense, superheated center, nowhere else in the Sun, making the core the true source of all the energy that eventually reaches Earth as sunlight. The conditions required for fusion are extraordinarily specific. Temperatures must be high enough to give hydrogen nuclei sufficient energy to overcome their electrical repulsion, and pressures must be high enough to force these nuclei close together despite their natural tendency to repel each other. Only in the Sun's core do these conditions exist, making this region the powerhouse of our entire solar system, the furnace that drives everything from Earth's weather to the growth of plants to the evolution of life itself. The core's density is about 150 times that of water, meaning that a cubic inch of core material, if you could somehow extract it and bring it to Earth, would weigh about 150 times more than a cubic inch of water, though it would immediately explode outward with tremendous force as the enormous pressure keeping it compressed was released. This density comes from the immense gravitational force of all the sun's mass pressing inward, compressing the core material until atoms are packed far more tightly than anything we experience on Earth. At this density, matter behaves in unusual ways, with the plasma responding to pressures and temperatures that exist nowhere naturally in our world, creating the unique environment where fusion can occur. Pressure in the core reaches 250 billion atmospheres, a force so immense that it crushes atomic nuclei together despite the fundamental electromagnetic force that normally keeps them apart. On Earth, we experience atmospheric pressure of about 14.7 pounds per square inch at sea level, a pressure we barely notice because we evolved under these conditions. In the Sun's core, the pressure is 250 billion times greater, a weight that would instantly crush any material from Earth into a dense plasma, forcing atomic nuclei so close together that they occasionally tunnel through the electromagnetic barrier and fuse, releasing energy and creating heavier elements in the process, the fundamental process powering our star. Energy created in the core takes somewhere between 10,000 and 170,000 years to reach the surface, as photons take a random walk through the dense radiative zone, bouncing countless times before finally emerging. A photon created by fusion in the core doesn't simply travel straight outward to the surface. Instead, it collides with particles of plasma, is absorbed and re-emitted in random directions, absorbed again, re-emitted again, in a chaotic journey that takes millennia to complete. This means that the sunlight warming your face today began its journey in the sun's core tens of thousands of years ago, long before recorded human history, a light that has finally completed its ancient voyage to reach us. The radiative zone extends from the core to about 70% of the sun's radius, forming the middle layer where energy moves outward primarily through radiation rather than convection. In this region, the plasma is still very hot and dense, though not as extreme as in the core, and photons of light slowly work their way outward through countless absorptions and re-emissions, gradually transporting the energy created by fusion toward the surface. The temperature decreases from about 12 million degrees Fahrenheit at the inner boundary to about 4 million degrees at the outer boundary, a gradual cooling that reflects the outward flow of energy through this vast glowing layer of stellar plasma. Energy moves through this region primarily as electromagnetic radiation in the form of high-energy photons that bounce from particle to particle in a process called radiative diffusion. Each photon travels a tiny distance before being absorbed by an ion or electron, then re-emitted in a random direction, making progress outward only very slowly. This is fundamentally different from how energy moves in the outer layers of the sun, where hot material physically rises and cool material sinks in a process called convection. The radiative zone is so dense that convection cannot occur here. Radiation is the only way energy can escape, creating this vast region where light itself struggles to move through the compressed plasma. Photons bounce countless times through this dense plasma, perhaps billions or trillions of times during their journey through the radiative zone, each collision changing the photon's direction and sometimes its energy. A high-energy gamma-ray photon created by fusion in the core will bounce so many times and lose energy in so many small increments that by the time it emerges from the radiative zone, it has been transformed into many lower-energy photons, from X-rays to ultraviolet light to visible light. This process is what makes the sun's surface cooler and less energetic than its core, a gradual transformation of energy from its most concentrated form to more diffuse and varied wavelengths. The temperature in the radiative zone ranges from 12 million degrees Fahrenheit at its inner boundary to about 4 million degrees at its outer edge, a steady decrease that reflects the outward flow of energy from the nuclear furnace at the center. Despite this cooling, even the coolest parts of the radiative zone remain far hotter than anything we experience on Earth, hot enough to keep all matter in a plasma state, with atoms stripped of their electrons and moving at tremendous speeds. This temperature gradient drives the outward flow of energy through radiation as the hotter inner regions emit more intensely than the cooler outer regions, creating a natural flow from core to surface that has continued for billions of years. This zone contains about 48% of the sun's total mass, nearly half of all the matter in our star compressed into this middle layer between the core and the outer convective zone. Despite occupying a significant volume, stretching from about 25% to 70% of the Sun's radius, the radiative zone is still dense enough to hold nearly half the Sun's mass, a testament to how compressed matter becomes under the immense gravitational forces at play in stellar interiors. This mass, primarily hydrogen and helium plasma, slowly transports energy outward through radiation, playing a crucial role in the Sun's energy production cycle, connecting the fusion furnace at the center to the roiling convective layer above. The convective zone is where hot plasma rises and cooler plasma sinks in enormous circulation patterns, creating massive currents that transport energy outward toward the surface through the physical movement of matter rather than radiation alone. Here, finally, the plasma is cool enough and diffuse enough that convection becomes the dominant means of energy transport. As buoyant hot material rises toward the surface, cools, and sinks back down in a continuous cycle. This roiling motion gives the Sun's surface its granular appearance when viewed at high resolution, with each granule representing the top of a convection cell where hot material reaches the surface and begins to cool, a dynamic, ever-changing landscape of flowing plasma. This creates massive convection currents, like boiling water on a vast scale, though the water is ionized plasma millions of degrees hot and the pot is thousands of miles across. These convection cells vary in size, from small granules about 600 miles across to supergranules tens of thousands of miles across, creating a hierarchy of circulation patterns that transport heat and momentum throughout the outer layers of the Sun. The physics is similar to what happens in a pot of water on a stove, where hot water rises from the bottom, cools at the surface, and sinks back down, but the scale and energy involved are vastly greater, creating a dynamic, turbulent region that shapes the Sun's visible surface. The convective zone extends from about 70% of the Sun's radius to the surface, encompassing roughly the outer 30% of the Sun's radius but containing only about 2% of the total mass, as the plasma here is much less dense than in the deeper layers. This is where the Sun transitions from the radiative transport of energy to convective transport, where the physical movement of hot and cool material becomes the primary way that energy reaches the surface. The convective zone is a turbulent, dynamic region where plasma flows in complex patterns, creating the magnetic fields that drive solar activity like sunspots, flares, and prominences, connecting the Sun's interior to the phenomena we observe from Earth. These convection cells create the granular appearance of the Sun's surface when viewed through powerful telescopes, revealing that what seems like a smooth, glowing disk is actually a constantly shifting pattern of bright and dark regions. Each bright granule represents hot plasma rising from below, reaching the photosphere and spreading outward before cooling and sinking back down at the darker boundaries between granules. These granules are typically about 600 miles across and last for only 10 to 20 minutes before breaking up and being replaced by new ones, creating a constantly changing landscape that reflects the vigorous convection happening just below the visible surface, a boiling cauldron of plasma that never rests. Each granule on the surface is typically about 600 miles across, roughly the distance from Los Angeles to Seattle, a scale that seems enormous by human standards, yet represents just a tiny cell in the vast convective zone below. These granules are the visible tops of convection cells, where hot plasma from the interior finally reaches the surface, cools slightly by radiating energy into space, and then sinks back down to be reheated and rise again. Watching a time-lapse of the Sun's surface reveals these granules constantly appearing, evolving, and disappearing, creating a shifting mosaic that reflects the turbulent energy transport happening throughout the outer layers of our star, a dynamic process that has continued for billions of years. The photosphere is the visible surface of the Sun we see from Earth, the layer from which light can finally escape into space after its long journey from the core. Below this level, the Sun is too opaque for light to travel freely. Above it, the gas becomes transparent enough that photons can stream outward unimpeded. The photosphere is only about 300 miles thick, a remarkably thin shell considering the Sun's enormous size. Yet this is the layer that defines the Sun's visible edge and produces most of the light that reaches Earth. When we measure the Sun's diameter or observe sunspots, we are looking at features in the photosphere, this interface between the Sun's interior and the space beyond. It's only about 300 miles thick, remarkably thin for such a massive body, like the skin on an apple compared to the fruit within. Yet this thin layer is what we see when we observe the sun. Above the photosphere, the gas becomes increasingly tenuous, forming the chromosphere and corona. Below it, the sun becomes increasingly opaque, with light unable to escape directly. This transition happens over just a few hundred miles, a tiny fraction of the sun's 864,000-mile diameter. The thinness of the photosphere means that the sun has a relatively sharp edge when viewed from Earth, though in reality there is no solid surface, just a gradual transition from opaque to transparent plasma. The photosphere gives the sun its yellowish-white color that we associate with our star, a color determined by its surface temperature of about 10,000 degrees Fahrenheit. At this temperature, the sun emits light across the entire visible spectrum, with its peak output in the yellow-green range, though our atmosphere and our eyes combine to make the sun appear more yellow or white depending on conditions. Hotter stars appear blue or white, while cooler stars appear orange or red. The sun's color places it in the middle of the stellar temperature range. This familiar color has illuminated Earth for billions of years, a steady beacon whose hue has remained essentially constant throughout the evolution of life on our planet. Sunspots appear as dark patches on the photosphere, regions that look darker not because they don't emit light, but because they're slightly cooler than their surroundings, typically about 6,500 degrees Fahrenheit compared to the photosphere's 10,000 degrees. These temperature differences make sunspots appear dark by contrast, even though if you could see a sunspot in isolation, it would glow brightly. Sunspots are caused by intense concentrations of magnetic field that inhibit convection, preventing hot plasma from rising to the surface in these regions and creating cooler, darker areas. They can persist for days or weeks, slowly changing shape as they're carried across the sun's face by its rotation, visible reminders of the powerful magnetic forces at work in our star. The photosphere emits most of the sun's visible light, the light that enables us to see, that powers photosynthesis in plants, that warms the Earth's surface during the day. This layer radiates energy across the entire electromagnetic spectrum, from radio waves to gamma rays, but its peak emission is in the visible range because of its temperature. The light from the photosphere takes just over 8 minutes to cross the space between the Sun and Earth, traveling at 186,000 miles per second, bringing energy that was created tens of thousands of years ago in the core, transported slowly through the interior and finally released from this thin, glowing shell to begin its journey across the solar system. The chromosphere sits just above the photosphere, a layer of the Sun's atmosphere about 1,200 miles thick that is normally invisible against the bright photosphere, revealed only during solar eclipses when the Moon blocks the photosphere's light. The chromosphere is slightly hotter than the photosphere, with temperatures ranging from about 7,000 to 35,000 degrees Fahrenheit, an increase that marks the beginning of the mysterious temperature rise toward the corona. Its name comes from the Greek word for color, because during eclipses it appears as a thin reddish-pink ring around the Sun, colored by hydrogen emission at a specific wavelength. This beautiful layer is home to spicules and other dynamic phenomena, a transition region between the visible surface and the million-degree corona above. It appears reddish during solar eclipses, giving it its name from the Greek word for color. A vivid crimson glow that circles the Sun when the Moon's disk blocks the bright photosphere. This red color comes from hydrogen atoms emitting light at a wavelength of 656 nanometers in the red part of the spectrum, a signature called the H-alpha line that astronomers use to study the chromosphere and other hydrogen-rich regions of space. For the brief moments of totality during an eclipse, this colorful layer becomes visible, a reminder that the Sun is not simply a uniform ball of light, but a complex atmosphere with multiple layers, each with its own characteristics, temperatures, and colors. This layer is about 1,200 miles thick, significantly thicker than the photosphere, but still just a thin shell compared to the Sun's overall size, extending upward from the visible surface into the increasingly hot and tenuous regions beyond. In the chromosphere, the temperature begins its mysterious rise, climbing from about 7,000 degrees at the base to perhaps 35,000 degrees at the top, though measuring temperatures in this dynamic, low-density layer is challenging. This temperature increase, counter to our expectation that things should cool as we move away from the heat source, hints at the energy transport mechanisms operating in the Sun's outer atmosphere, where magnetic fields and waves carry energy upward, heating the gas to temperatures that eventually reach millions of degrees. Temperature in the chromosphere ranges from 7,000 to 35,000 degrees Fahrenheit, a significant increase from the photosphere below, marking the beginning of the Sun's atmospheric temperature inversion, where temperatures rise as you move away from the visible surface. This heating is believed to be caused by the dissipation of magnetic energy and acoustic waves traveling upward from the convective zone below, energy that is absorbed by the chromosphere's thin gas, raising its temperature. The chromosphere represents a transition region where the character of the Sun's atmosphere begins to change dramatically, from the relatively cool, dense photosphere to the million-degree corona above, a gradient that has fascinated solar physicists for generations. Spicules, jets of gas, constantly shoot up from the chromosphere, reaching heights of several thousand miles before falling back down, each one lasting only a few minutes but replaced by new ones in a continuous cycle across the Sun's surface. At any given time, tens of thousands of spicules dot the Sun's limb, visible as a forest of plasma jets extending upward into the chromosphere and beyond. These structures follow magnetic field lines, with hot plasma rising along the fields and then cooling and falling back, creating the characteristic needle-like appearance that gives spicules their name. They represent one way that energy and matter are transported between the photosphere and the upper atmosphere, connecting the visible surface to the corona above. The corona is the Sun's outer atmosphere, visible during total solar eclipses as a pearly white halo extending millions of miles into space, with streamers and loops that follow the Sun's magnetic field lines. This tenuous outer layer is so faint compared to the photosphere that it's normally invisible, overwhelmed by the bright surface below. But during an eclipse, when the moon blocks the photosphere, the corona springs into view in all its ethereal beauty. Ancient observers called it the crown, from which we get the name corona, recognizing its regal appearance around the darkened Sun. The corona is home to some of the Sun's most dramatic phenomena, from coronal mass ejections to the steady solar wind that streams outward through the solar system. It extends millions of miles into space, far beyond the visible disk of the Sun, with no clear outer boundary but instead gradually fading into the solar wind that fills the solar system. The corona's structure changes with the solar cycle, appearing relatively simple and symmetric during solar minimum, with large streamers extending from the equatorial regions, and more complex and irregular during solar maximum, when intense magnetic activity creates a chaotic, ever-changing structure. Spacecraft that fly through the corona, like the Parker Solar Probe, are exploring this region directly for the first time, measuring its temperature, density, and magnetic fields, helping us understand this mysterious and beautiful layer of our star's atmosphere. The corona's temperature mysteriously exceeds 2 million degrees Fahrenheit, a finding that initially shocked astronomers when it was discovered in the mid-20th century, as it seems to violate the basic principle that heat flows from hot to cold. The photosphere below is only about 10,000 degrees, yet somehow the corona, much farther from the Sun's core, reaches temperatures hundreds of times higher. This coronal heating problem remained one of the great mysteries of solar physics for decades, though scientists now believe the answer involves magnetic fields carrying energy from below, either through magnetic reconnection events or through the dissipation of magnetic waves, heating the tenuous coronal gas to these extreme temperatures despite its distance from the Sun's interior furnace. Scientists are still working to fully understand why the corona is hotter than the surface, though the leading explanations involve magnetic fields threading through the corona and carrying energy upward from the convective zone below. These fields can store enormous amounts of energy, and when they reconnect or when waves travel along them, this energy can be released as heat, warming the corona's tenuous gas to millions of degrees. The Parker Solar Probe and other spacecraft are currently studying the corona up close, making measurements that will help resolve this mystery. Understanding coronal heating is not just an academic question. It helps us predict space weather and understand stellar atmospheres throughout the universe, wherever similar physics operates. The corona constantly streams particles into space as the solar wind, a flow of charged particles that extends throughout the solar system and beyond, carrying the Sun's influence far from its visible disk. This wind consists primarily of electrons and protons, along with heavier ions, all moving at speeds ranging from about 250 to 750 miles per second, fast enough to cross the distance from Sun to Earth in just a few days. The solar wind shapes the magnetic environments of planets, creates auroras when it interacts with Earth's magnetic field, and defines the boundary of the heliosphere, the bubble of solar influence within which all planets orbit. It's a constant reminder that the Sun is not isolated, but actively influences its entire neighborhood. Sunspots are cooler, darker regions on the Sun's surface, appearing as blemishes on the photosphere when viewed through a properly filtered telescope, though they're still hotter and brighter than most objects in the universe. These features have been observed for centuries, with systematic records dating back to the early 1600s when telescopes were first pointed at the Sun, revealing that our star's face is not perfect and unchanging, but marked by these mysterious dark spots that appear and disappear over weeks and months. Sunspots typically appear in pairs or groups, with complex magnetic fields threading through and around them, and they're often accompanied by other solar activity like flares and prominences, making them centers of dramatic solar phenomena. These spots are caused by intense magnetic activity that inhibits the normal convection of hot plasma to the surface, creating regions that are about 3,500 degrees cooler than their surroundings. The strong magnetic fields in sunspots are thousands of times more powerful than Earth's magnetic field, strong enough to affect the motion of charged particles and suppress the convective cells that normally bring hot material to the photosphere. Without this constant supply of fresh, hot plasma, the sunspot regions cool slightly, making them appear darker by contrast. The magnetic fields in sunspots are so strong that they can sometimes be seen in observations as they organize the plasma into intricate patterns, revealing the invisible forces shaping the sun's surface. Sunspots can be larger than Earth itself, with the biggest groups spanning tens of thousands of miles across and containing multiple individual spots with complex internal structure. A large sunspot group might contain a dozen or more individual spots, each with its own magnetic polarity, arranged in intricate patterns that reflect the magnetic field configuration below the surface. These massive features rotate with the Sun, taking about 25 days to cross the visible disk at the solar equator, allowing astronomers to track individual sunspot groups from appearance to disappearance. When viewed up close, sunspots show remarkable detail, with dark central regions called umbrae surrounded by lighter penumbrae, where magnetic fields are organized into radial filaments extending outward from the center. The number of sunspots rises and falls in an approximately 11-year cycle, a pattern discovered in the mid-1800s by amateur astronomer Heinrich Schwabe after years of patient observation and record-keeping. This cycle reflects variations in the Sun's magnetic field, which strengthens, weakens, and reverses polarity with this roughly decade-long rhythm. During solar maximum, when sunspot numbers peak, the Sun's surface can be dotted with numerous large spot groups and is much more active, with frequent flares and prominences. During solar minimum, the Sun can go days or weeks with no spots at all, appearing calmer and more uniform. This cycle affects space weather, auroral activity, and even subtle influences on Earth's upper atmosphere. Sunspot activity affects space weather and can impact Earth's technologies, particularly satellites, power grids, and communication systems that are vulnerable to the increased radiation and charged particles associated with active regions on the Sun. During periods of high sunspot activity, solar flares and coronal mass ejections become more common, sending bursts of energy and matter toward Earth that can disrupt GPS signals, interfere with radio communications, and even induce currents in power lines that can damage transformers. Space agencies and power companies now monitor solar activity closely, using networks of ground and space-based observatories to watch for dangerous eruptions and issue warnings when necessary, treating the Sun's weather as a practical concern affecting our technology-dependent civilization. Solar flares are massive explosions on the Sun's surface, sudden releases of energy equivalent to millions of nuclear bombs detonating simultaneously. Bright flashes that erupt from active regions in minutes and fade over an hour or more. These flares occur when magnetic field lines in the Sun's atmosphere become twisted and stressed by the roiling motions of the plasma below, building up energy until the fields suddenly reconnect in an explosive release. The energy appears as intense bursts of radiation across the electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays, along with accelerated particles that stream away from the flare site at significant fractions of light speed, creating a complex event that affects the entire near-Sun environment. They release energy equivalent to millions of nuclear bombs, though the energy manifests primarily as electromagnetic radiation and accelerated particles rather than explosive blast waves, since there's no air in space to carry a shock wave. The largest flares, classified as X-class, can release 1,025 joules of energy or more, equivalent to detonating millions of megatons of TNT in a matter of minutes. This energy comes from the magnetic field, which stores energy like a compressed spring until a critical point is reached and the field suddenly reconfigures, converting magnetic energy into heat, light, and kinetic energy of particles in an explosive instant that can briefly outshine the entire Sun at X-ray wavelengths. Flares occur when magnetic field lines suddenly reconnect, a process where oppositely directed field lines come together, cancel each other out, and reform in a lower energy configuration, releasing the energy difference as an explosion. This reconnection can happen when the Sun's rotation and convection twist and stress the magnetic field until it becomes unstable, or when new magnetic flux emerges from below the surface and interacts with existing fields. The reconnection process itself is rapid, taking place in seconds or minutes, but the consequences last much longer, as the released energy heats plasma to tens of millions of degrees, accelerates particles to near light speed, and sends radiation streaming across the solar system. These eruptions can affect radio communications on Earth, particularly high-frequency radio used for long-distance communication, aviation, and maritime operations, as the intense X-rays and ultraviolet light from the flare ionize Earth's upper atmosphere, changing its radio-reflecting properties. During major flares, radio blackouts can occur on the sunlit side of Earth, lasting from minutes to hours until the atmosphere returns to normal. Airlines flying polar routes where radio communication is essential and alternatives are few sometimes reroute flights during major solar storms to avoid communication blackouts. Ham radio operators, conversely, sometimes welcome solar activity because it can enhance long-distance communication on certain frequencies, showing how the Sun's influence on our atmosphere creates both challenges and opportunities. Solar flares travel at the speed of light, reaching Earth in about 8 minutes, the same time it takes light to make the journey, meaning that we see the flare at essentially the same moment its radiation arrives to affect our atmosphere. This is significantly faster than the particles associated with coronal mass ejections, which take 1 to 3 days to reach Earth, giving solar forecasters very little warning time for flare effects. Spacecraft monitoring the Sun can observe flares as they happen and send alerts, giving satellite operators and power companies minutes to prepare, though 8 minutes isn't much time to take protective measures. This is why continuous monitoring of the Sun has become crucial for our technological infrastructure, providing what little warning time is possible for these light-speed events. Coronal mass ejections, or CMES, are massive bursts of solar wind and magnetic fields rising above the solar corona and being released into space. Events separate from solar flares, though the two often occur together from the same active region. A CME involves the actual ejection of plasma, billions of tons of matter hurled away from the Sun at speeds ranging from hundreds to thousands of miles per second, carrying embedded magnetic fields that can interact dramatically with Earth's magnetosphere when they arrive. These events appear in coronagraph images as bright expanding clouds moving outward from the Sun, though the CME itself is invisible to the eye, visible only because the plasma scatters sunlight. CMEs are among the most dramatic events in the solar system, reshaping the Sun's corona and sending shockwaves through space. A single CME can eject billions of tons of matter into space, with estimates for large events ranging from 10 billion to 100 billion tons or more of plasma launched away from the Sun in a matter of hours. This represents a tiny fraction of the Sun's total mass, insignificant to the star itself, yet enormous by human standards and carrying enough energy to affect the entire inner solar system. The plasma in a CME consists primarily of electrons and protons, along with heavier ions, all moving together as a magnetized cloud that expands as it travels outward. When such a cloud reaches Earth, it compresses our magnetic field, inducing currents in the upper atmosphere and creating the beautiful auroras we see at high latitudes. These events can trigger beautiful auroras when they reach Earth, as the charged particles from the CME interact with our planet's magnetic field, funneling down toward the poles. neutrons and colliding with atoms and molecules in the upper atmosphere. These collisions excite the atmospheric gases, causing them to emit light at characteristic wavelengths. Oxygen produces green and red light, while nitrogen produces blue and purple. During major geomagnetic storms caused by powerful CMEs, auroras can be seen at much lower latitudes than usual, sometimes visible from the northern United States or even further south. These dancing lights have inspired myths and legends throughout human history, now understood as visible evidence of our star's reach across space to touch our world. Strong CMEs can potentially disrupt power grids and satellites, with historical events demonstrating the vulnerability of our technological infrastructure to major space weather. The most famous case occurred in 1859, known as the Carrington event, when a powerful CME caused telegraph systems worldwide to fail, with operators reporting sparks, shocks, and even fires from their equipment, though this was decades before our modern electrical grid existed. In 1989, a geomagnetic storm caused by a CME knocked out power to 6 million people in Quebec for 9 hours, when induced currents damaged transformers in the power grid. Today, with our dependence on satellites for communication, navigation, and weather forecasting, and with intercontinental power grids, the potential impact of a major CME is even greater, which is why space weather forecasting has become increasingly important. CMEs travel more slowly than solar flares, taking 1 to 3 days to reach Earth depending on their speed, with typical travel times around 24 to 48 hours for the billion-ton plasma clouds to cross the 93 million miles between Sun and Earth. This delay, in contrast to the 8-minute light-speed arrival of flare radiation, gives forecasters valuable time to issue warnings and prepare for potential impacts. Spacecraft positioned between the Sun and Earth, particularly at the L1 Lagrange point about 1 million miles from Earth, can detect an approaching CME about 30 to 60 minutes before it reaches our planet, providing a final warning that allows satellite operators to put spacecraft in safe modes and power companies to prepare for possible disturbances, a modern early warning system for solar storms. The Sun constantly emits a stream of charged particles called the solar wind, a flow that never stops, day or night, decade after decade, a continuous outpouring of the Sun's substance into the surrounding space. This wind consists primarily of electrons and protons, the components of hydrogen atoms stripped apart by the corona's extreme heat, along with small amounts of heavier ions like helium, carbon, and iron. The solar wind is tenuous compared to Earth's atmosphere, with only a few particles per cubic centimeter in the near-Earth environment. Yet over the vast distances and times involved, this wind carries away about 1 million tons of material from the Sun every second, a loss that sounds dramatic but represents an insignificant fraction of the Sun's total mass. This wind travels at speeds of about 900,000 miles per hour on average, though the speed varies considerably, with slow solar wind moving at around 250 miles per second and fast solar wind reaching 500 miles per second or more. The fast wind tends to originate from coronal holes, regions of the corona where magnetic field lines open into space rather than looping back to the surface, allowing plasma to stream outward unimpeded. The slow wind comes from other regions, including the edges of coronal streamers. These different wind streams interact as they travel outward, creating compression regions and rarefications that structure the solar wind into a complex, dynamic medium that fills the space between planets, carrying the Sun's magnetic field and influence throughout the solar system. The solar wind extends far beyond Pluto, creating the heliosphere, a bubble of solar influence that encompasses all the planets and extends perhaps 100 astronomical units or more from the Sun until it finally meets the interstellar medium and forms a boundary called the heliopause. The Voyager spacecraft, launched in 1977, crossed this boundary in the 2010s, becoming the first human-made objects to enter interstellar space, the region beyond the Sun's direct influence. Even at those enormous distances, billions of miles from the Sun, the spacecraft detected signs of the solar wind and the Sun's magnetic field before finally crossing into the true space between stars. The heliosphere protects the inner solar system from galactic cosmic rays, acting as a shield against high-energy particles from beyond our solar system. It shapes the magnetic fields of planets in our solar system, compressing the day side of planetary magnetospheres and stretching them into long tails on the night side, creating the characteristic teardrop shapes seen in models of Earth's magnetic environment. The solar wind's pressure on Earth's magnetic field creates the Van Allen radiation belts, regions of trapped particles that can be hazardous to spacecraft and astronauts. For planets without strong magnetic fields, like Mars, the solar wind can interact directly with the upper atmosphere, gradually stripping it away over geological time. Venus has no global magnetic field, but creates an induced magnetosphere where the solar wind drapes around the planet. Each planet's interaction with the solar wind is unique, creating a variety of magnetospheric environments throughout the solar system. The solar wind creates the distinctive tails of comets, pushing gas and dust away from the comet's nucleus and forming two separate tails. A blue ion tail pointing directly away from the Sun, shaped by the solar wind, and a white dust tail curved along the comet's orbit. The ion tail forms when ultraviolet light from the Sun ionizes gases in the comet's coma, creating charged particles that are picked up by the solar wind and carried away in a straight line directly away from the Sun, regardless of the comet's direction of motion. This is why comet tails always point away from the Sun, not behind the comet's motion as you might expect. Watching a comet's tail change as it orbits the Sun reveals the invisible wind constantly flowing from our star. The Sun rotates on its axis, but not as a solid body, spinning instead like the gas giant planets where different latitudes rotate at different speeds. This differential rotation is possible because the Sun has no solid surface to lock it into uniform motion. The plasma at different latitudes can move independently, creating a complex rotation pattern. Solar astronomers can measure this rotation by tracking features like sunspots as they move across the Sun's disk, measuring how many days it takes for a spot to return to the same position after the Sun completes one rotation. Galileo made some of the first such measurements in the early 1600s, using sunspot observations to prove that the Sun rotates, a finding that challenged prevailing ideas about celestial perfection. The equator completes one rotation in about 25 Earth days, the fastest rotation rate anywhere on the Sun, with the plasma at the equator moving at roughly 4,500 miles per hour at the surface. This 25-day period is measured relative to the distant stars. From Earth's perspective, because we're also orbiting the Sun, it appears to take about 27 days for features to return to the same apparent position, a difference that confused early observers until they understood the geometry. The rapid equatorial rotation contributes to the Sun's magnetic field generation through the solar dynamo, where the combination of differential rotation and convection creates and maintains the complex magnetic field that drives so much of the Sun's activity and variability over time. The polar regions take approximately 35 days to complete a rotation, moving more slowly than the equator and creating a rotational shear between different latitudes as the equator outraces the poles. This 10-day difference from equator to pole represents a significant shear in the plasma flow, and this differential rotation plays a crucial role in generating the Sun's magnetic field by stretching and twisting field lines, winding them up like rubber bands until they become unstable and burst through the surface as sunspots and active regions. The exact mechanism of the solar dynamo remains an area of active research, but differential rotation is clearly a key component, transforming weak poloidal fields into strong toroidal fields wrapped around the Sun beneath the surface. This differential rotation is possible because the Sun is made of plasma, not solid material, allowing different parts to move independently without shearing stress building up the way it would in a solid body. The Sun's interior is in constant motion, with convection cells rising and sinking, and this fluid nature allows the complex flow patterns we observe, including not just differential rotation but also meridional circulation, where material flows from equator to poles near the surface and from poles to equator deeper down, a slow overturning circulation that takes decades to complete one cycle and helps transport magnetic field and angular momentum through the Sun's interior. The Sun's rotation helps generate its powerful magnetic field through a process called the solar dynamo, where the combination of rotation, particularly differential rotation and convective motion, transforms and amplifies magnetic fields in a self-sustaining cycle. Weak magnetic fields are stretched by differential rotation wrapped around the Sun to create strong toroidal fields, while convection creates turbulence that twists and concentrates these fields. Rising convection cells bring fields to the surface where they emerge as active regions, sunspots, and larger-scale patterns. The cycle continues, with the field reversing every 11 years as part of the 22-year magnetic cycle, creating the rhythmic solar activity that has been observed for centuries and continues to fascinate researchers seeking to understand stellar magnetism. The Sun has a complex, ever-changing magnetic field that pervades its interior, atmosphere, and the space surrounding it, extending throughout the solar system as the interplanetary magnetic field carried by the solar wind. This field is not a simple dipole like Earth's magnetic field, but instead shows complex multipole structure with regions of opposite polarity scattered across the surface, particularly during solar maximum when the field is most disordered. The field emerges from the interior in active regions, forming loops that extend through the chromosphere and corona, channeling plasma and energy, creating the structures we see during eclipses as streamers and coronal loops, a visible manifestation of these invisible forces shaping the Sun's outer atmosphere. This field flips approximately every 11 years, with the Sun's north magnetic pole becoming the south pole and vice versa, though the flip is not a sudden event but rather a gradual transition taking a year or more to complete. This polarity reversal occurs near solar maximum, when the field is most complex and disordered, and marks the midpoint of the 22-year magnetic cycle, sometimes called the Hale cycle after the astronomer George Ellery Hale, who discovered the magnetic nature of sunspots. After two 11-year sunspot cycles, the magnetic field returns to its original polarity, completing the full cycle. This periodic reversal is a consequence of the solar dynamo process, where the field is continually regenerated and transformed by the Sun's rotation and convection. The magnetic field drives most solar activity, including sunspots and flares, with magnetic energy stored in twisted and stressed field configurations being suddenly released in explosive events that can affect the entire solar system. Sunspots form where strong magnetic field bundles emerge through the surface, inhibiting convection and creating cooler regions. Solar flares occur when these fields reconnect, converting magnetic energy into heat and accelerated particles. Prominences and filaments follow magnetic field lines, showing us the field's structure. Coronal mass ejections tear away portions of the field and fling them into space. Understanding the Sun's magnetic field is thus key to understanding and predicting solar activity, space weather, and the Sun's influence on Earth and the other planets. Magnetic field lines can loop high above the surface, creating prominences, massive arches of relatively cool, dense plasma suspended in the hot, tenuous corona by magnetic forces. These structures can tower hundreds of thousands of miles above the surface, dwarfing Earth in size, yet they persist for weeks or months because the magnetic field supports them against gravity. The plasma in prominence follows the field lines, flowing along the arches from one foot point to another, sometimes falling back to the surface in spectacular cascades when the structure becomes unstable. Prominences are most easily visible at the Sun's limb during eclipses, appearing as bright red or pink loops extending beyond the edge of the Moon's disk, though specialized telescopes can see them on the disk as dark filaments. The Sun's magnetic field extends throughout the entire solar system, carried outward by the solar wind as the interplanetary magnetic field, a vast structure that rotates with the Sun, forming a spiral pattern called the Parker spiral after the physicist Eugene Parker, who predicted its shape. This field influences all the planets, interacting with their magnetospheres, channeling cosmic rays, and structuring the heliosphere. Even at Earth's orbit, 93 million miles from the Sun, we're embedded in the Sun's magnetic field, typically measuring a few nanotesla in strength, thousands of times weaker than Earth's surface field, but still measurable and important for space weather. This extended magnetic field is part of what makes the Sun more than just a point source of light and heat, but a dynamic presence that influences its entire neighborhood. Prominences are large, bright loops of plasma extending from the surface, magnificent structures visible during solar eclipses as pink or red arcs reaching far above the Sun's limb, though they can also be seen with specialized telescopes that filter for specific wavelengths of light even when the Sun's disk is visible. These features are relatively cool compared to the surrounding corona, typically about 10,000 degrees rather than the corona's million-plus degrees, and much denser, making them visible against the hot but tenuous coronal background. Prominences form along boundaries between regions of opposite magnetic polarity, where the field creates loops that can support dense material against gravity. They can remain stable for days or weeks, slowly evolving until eventually they either fade away or erupt outward in spectacular eruptions. They follow the Sun's magnetic field lines, with the plasma confined to flow along these invisible tracks, unable to move perpendicular to the field because the charged particles are tied to the field. This magnetic confinement is what allows prominences to extend so far above the surface without falling back immediately. Gravity pulls the plasma down, but the magnetic field supports it, creating a balance that can persist for extended periods. Watching time-lapse videos of prominences reveals the plasma flowing along the field lines, sometimes rising, sometimes falling, creating dynamic shapes that evolve over hours and days. The field lines act like tracks constraining the plasma's motion, making the invisible magnetic field visible through the bright material it guides and supports. Some prominences can persist for weeks or even months, relatively stable structures in the otherwise dynamic solar atmosphere, though they slowly evolve, with material flowing along the magnetic field lines, some plasma falling back to the surface while fresh material rises to take its place. The largest prominences can contain billions of tons of plasma suspended above the surface, held aloft by magnetic forces. Eventually, most prominences either gradually dissipate as the supporting magnetic field weakens or changes configuration, or they erupt outward in a prominence eruption, which can become a coronal mass ejection if the field breaks open and allows the material to escape into space, sending that suspended plasma streaming outward toward the planets at speeds of hundreds of miles per second. These structures can tower hundreds of thousands of miles above the surface, with the largest extending 10 to 20 times Earth's diameter from the photosphere, creating arches so vast that multiple Earths could fit within a single loop. When viewed from the side at the Sun's limb, prominences appear as graceful arches or curtains of glowing gas. When viewed from above against the Sun's disk, the same structures appear as dark filaments, absorbing light against the bright photosphere. This difference in appearance is simply a matter of viewing angle and contrast. The prominence material is cooler and denser than its surroundings, so it emits less light than the hot corona around it, but more than empty space, creating this reversal in appearance depending on the background. When a prominence is seen against the dark background of space, we call it a prominence. When that same structure is seen against the bright disk of the Sun, we call it a filament, two names for the same physical feature observed under different viewing conditions. Filaments appear dark because the prominence material, though hot by earthly standards at 10,000 degrees, is much cooler than the 10,000-degree photosphere behind it, so it absorbs more light than it emits, creating a dark line or region on the Sun's face. Both prominences and filaments help map the Sun's magnetic field, as they always form along boundaries between regions of opposite polarity, making them useful tracers of the large-scale magnetic structure underlying solar activity. The Sun orbits the center of the Milky Way galaxy, moving through space at tremendous speed, part of a vast cosmic dance involving hundreds of billions of stars all orbiting the galactic center, bound by gravity to this immense spiral structure. Our solar system is located in a minor spiral arm called the Orion Spur, about 26,000 light-years from the galactic center, roughly halfway from the center to the outer edge of the galactic disk. The Sun's orbit is not perfectly circular but slightly elliptical, and as it travels it also bobs up and down through the galactic plane, like a horse on a carousel, oscillating north and south of the midplane with a period of about 64 million years, adding another layer of motion to our star's journey through space. It takes about 225 to 250 million years to complete one galactic orbit, a period sometimes called a cosmic year or galactic year, representing the Sun's orbital period around the Milky Way's center. This means that since the Sun formed 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy, witnessing the slow evolution of galactic structure over cosmic time. Dinosaurs lived during the previous galactic summer, which was about 200 million years ago. The Sun has traveled roughly 1/3 of the way around the galaxy since they walked the Earth. This vast timescale provides perspective on our cosmic address, reminding us that while the sun seems eternal from a human perspective, it too is in motion through a much larger structure, part of a galaxy containing some 200 to 400 billion stars. The sun travels through the galaxy at roughly 514,000 miles per hour relative to the galactic center, a speed that seems enormous compared to our everyday experience, yet is typical for stars in our region of the galaxy. This motion is in addition to the sun's movement through space relative to nearby stars, which averages about 43,000 miles per hour, creating a complex velocity with components in multiple directions. The sun is also moving relative to the cosmic microwave background, the relic radiation from the Big Bang, at about 230 miles per second, or roughly 828,000 miles per hour. These different reference frames illustrate that motion is always relative, and the sun's speed depends on what we're measuring against, from nearby stars to the galactic center to the universe itself. It oscillates up and down through the galactic plane as it orbits, moving above and below the Milky Way's midplane in a bobbing motion with a period of about 64 million years, taking roughly 32 million years to travel from maximum height above the plane to maximum depth below it. Currently, the sun is moving northward through the galactic plane, having crossed the midplane about 3 million years ago. Some scientists have speculated that this oscillation might influence Earth's climate or extinction events by exposing our solar system to different densities of interstellar material or cosmic rays as we move through the galaxy. Though the evidence for such effects remains controversial and the mechanisms uncertain, a reminder that our cosmic environment is more complex than it might first appear. The Sun has completed about 20 orbits since its formation 4.6 billion years ago, meaning that our star has witnessed the slow evolution of the galaxy over many revolutions, seeing changes in galactic structure, the birth and death of neighboring stars, and the gradual chemical enrichment of the interstellar medium. Each orbit takes about 225 to 250 million years, so simple division gives us roughly 18 to 20 complete orbits, depending on the exact values used. During these orbits, the Sun has passed through various galactic neighborhoods, encountering different stellar populations and interstellar environments. The Sun formed from material enriched by previous generations of stars, and in turn, when the Sun dies billions of years from now, it will return enriched material to the interstellar medium, contributing to future generations of stars and planets in an ongoing cycle of stellar birth and death. In about 5 billion years, the Sun will exhaust its hydrogen fuel in the core, ending its main sequence lifetime and beginning a dramatic transformation that will fundamentally alter its character. When the core hydrogen is gone, fusion will cease in the center and the core will begin to contract under gravity, heating up as it shrinks. This heat will cause hydrogen in a shell surrounding the core to ignite, creating a shell-burning phase where fusion occurs in a thin layer rather than throughout the core. The energy from this shell burning will cause the Sun's outer layers to expand dramatically, beginning the transformation into a red giant, a phase that will last several 100 million years and will dramatically affect all the inner planets, changing our solar system's environment forever. It will then expand into a red giant, with its outer layers reaching Earth's current orbital distance, though whether our planet will be engulfed or pushed outward as the Sun loses mass remains a fascinating question among astronomers. As the Sun becomes a red giant, its radius will increase by a factor of perhaps 200, making it large enough to engulf Mercury and Venus, while Earth sits right at the boundary of uncertainty. Models suggest the Sun will lose perhaps 30% of its mass during the red giant phase, reducing its gravitational pull and allowing planets to spiral outward to larger orbits. Whether this outward drift is enough to save Earth from engulfment, or whether tidal forces and drag through the Sun's extended atmosphere will doom our planet, remains a subject of debate and ongoing research. After the red giant phase, it will shed its outer layers in a series of pulses, creating a planetary nebula, a beautiful expanding shell of gas enriched with the products of nuclear fusion from the Sun's interior. These layers will drift away over thousands of years, lit by the hot core left behind, creating one of the most beautiful sights in the universe as the expelled material fluoresces in the ultraviolet light from the central star. Planetary nebulae, despite their name, have nothing to do with planets. They're called that because early telescopes showed them as disc-shaped objects that resembled planets. though we now know they're the discarded outer envelopes of dying stars, spreading the elements forged in stellar interiors back into the galaxy to become raw material for future stars and planets. The remaining core will become a white dwarf, slowly cooling over trillions of years, a dense cinder of carbon and oxygen about the size of Earth but with roughly half the Sun's original mass, supported not by fusion or thermal pressure but by electron degeneracy pressure, a quantum mechanical effect that prevents the electrons from being compressed further. This white dwarf will be initially very hot, perhaps 100,000 degrees or more at its surface, glowing intensely despite producing no new energy through fusion. Over billions and trillions of years, it will radiate away its stored heat, gradually cooling and dimming, fading from white to yellow to red to eventually complete darkness, a stellar corpse that will persist for unimaginable spans of time, long after the last stars have ceased to shine. Eventually, the sun will fade to a black dwarf, though the universe isn't old enough for any to exist yet, as even the oldest white dwarfs are still glowing faintly, having not yet had time to cool completely in the 13.8 billion years since the Big Bang. A black dwarf is the theoretical final state of a white dwarf star, completely cold and dark, no longer emitting any light or heat, just a sphere of dense, inert carbon and oxygen drifting through space. It will take perhaps 1015 to 1020 years for the sun's white dwarf to cool to this state, time periods so vast they dwarf the current age of the universe, a future so distant that the very concept of stars may no longer apply, a reminder of the universe's deep time, stretching far beyond our ability to truly comprehend. And so we've journeyed through 100 facts about our star, this blazing sphere that has warmed our world for billions of years and will continue shining for billions more. A steady presence in our sky, a cosmic companion on Earth's journey through space. As you settle now into rest, let these thoughts drift gently away, knowing that somewhere above, the sun continues its ancient dance, its light beginning the journey toward tomorrow's dawn, as it has for ages past and will for ages yet to come. Good night.